Well, good morning there, students. Hey, it's Thursday, April 30th, 2020. Got just a little bit of a kind of a wrap-up video. Today's is a little bit of a hodgepodge. I don't think it'll be very long, but a couple details we need to wrap up for you to be able to answer some of the questions on your test. All right, so three things we're going to look at. We've been doing some work towards how do we figure out where an earthquake actually happens, and we're going to finish that off today with how can you can triangulate the location of an epicenter. And remember tri, that prefix means three, right? A triangle has three sides. So there's going to be something about three in there. We're going to look just briefly at how you describe the size of earthquakes. What's the rating? When you watch the news, they always say, the earthquake measured such and such on the Richter scale. Well, what does that mean? And we're going to talk a little bit about tsunamis. I'd like you to be able to explain how a tsunami occurs and why it is so destructive, one of the most destructive forces that ever happens on Earth. So let's look at how we locate this earthquake. So here's what we've already talked about. We have seismic waves get released when an earthquake happens, when there's that slip in the ground, and it sends out P waves and it sends out S waves, and the P waves travel a little bit faster, the S waves are a little slower. So when we have a seismic monitoring station, let's say an earthquake happened out here, and at some point, boom, the seismograph starts to wiggle a little bit. That's when the P waves got there, and then later it starts wiggling some more when the S waves get there. Okay, and then after that we get some surface waves and things like that. And certainly I'm not a trained geologist. I don't know all the details of this, but we're looking for those two jumps in there. And if we have this on a time scale, this piece of paper was moving through the seismograph when this started and this started, and we can record the times. Now when we look at that difference in the time, and we can compare it to a plot that's been made, and I had you do some of this. So for example, if I look at this scale over here and say, all right, that little line I drew represents 3 minutes on that vertical scale. Oops. And if I take this to where it matches up on here to 3 minutes, so there's a 3-minute gap between the P wave arrival and the S wave arrival, I can look at the bottom and say, oh, that was about, this one's, I gotta look at my scale. The examples I gave you were in kilometers. This one's in miles. This says about 900 miles. All right, so if I had a longer time difference, so this one I believe is a 5-minute gap. Okay, I follow up to where, and my graph doesn't want to behave real nice, but it's looking to me like that one would be about 2,100 miles. So based on the time difference between the P and S, I can figure out how far away it is. We got to do a third step. And this is where the triangulation part. So let's say right there in the far western corner of Nebraska, we have a seismic monitoring station. And it picked up an earthquake. It measured the P waves, it measured the S waves, and you calculate that the epicenter is a certain distance away. The problem is we don't know which direction. So we take this map and we draw a circle. That circle represents all the points that are that certain distance from that epicenter. So we know that the earthquake happened somewhere on the circle, but we don't know if it was up here, we don't know if it was over here, right? It could have happened in any one of 5 different states. But we've got other seismic monitoring stations. So here's a station down in Texas that picked up the signal from the same earthquake, but it picked up a different time, and in particular the difference between P and S waves. So from the difference in those P and S waves, we calculate how far the epicenter was from that station, and we get a circle. So we know it's this far from this station, and we know it's this far from this station, and if you notice, those two circles overlap in 2 points. So the earthquake must have happened either right over here in Wyoming, or it happened over here in South Dakota. Okay. How do we figure out which one? We need a third station, hence triangulation. So I got another station over here in California. We measure when the P wave arrival and the S wave arrival, we take the difference, figure out how far away it is, and we draw that circle. And the point at which all three overlap tells us the epicenter of that earthquake. Now, could we have more stations? Sure. And I imagine the more stations you have, the more accurately you can pinpoint that. But 3 stations is the minimum you need to be able to say where the earthquake actually happened. Now, you can also kind of correspond to what kind of damage happened in different places too. But if we want to try to pinpoint that earthquake, we need 3 stations. That's triangulation. Now, I would normally have you do an activity with this. The problem is, I don't know how many of you have a compass at home to draw, and most of the compasses that you buy, the cheap ones, don't work very good anyway. I tried making my own at home, and it kind of works. I made a great big compass out of a couple pieces of plywood. So I don't have you practicing that, but at least you should know the definition of triangulation and, be able to recognize that. Oh, where the 3 circles overlap, that's our epicenter. All right, let's go on to that second point, measuring the earthquake. So, you hear about the Richter scale. The Richter scale is based on the amplitude of the largest wave. So amplitude means size. If I take us back just briefly to when you see this seismogram. Now look, right here. This was the biggest wiggle. Okay? What the Richter scale does is basically says what was the biggest wiggle and compares earthquakes against each other. Okay? The bigger that wiggle, the bigger the amplitude of that biggest wave, that's how we determine that earthquake size. The Richter scale is a numeric scale, and each point on the scale represents a quake that's 10 times bigger. Okay? So if we have a 7.9 earthquake and a 6.9 earthquake, the 7.9 is 10 times bigger. So when you have earthquakes of Richter scale 3 and 4 happen all the time. And they do little damage, and quite often, nobody even notices that they happen. You start getting up to a Richter scale of 6, I think that's, at 6, you're going to notice probably some damage going on. When you get up to the 7 to 8 range, you're talking about major earthquakes. And not, anything, when you get up to close to 9 and over 9, those are monsters. Those are absolute monsters. And I should have looked before I did this, but I think the strongest that we've ever recorded, I believe, was a 9.2. Okay? Movies, the movies like to get into what does the 10.0 look like? The 10.0 would be crazy. Massive, massive destruction. So, think about it. An 8 is considered a major earthquake, and a 9 is 10 times more powerful than an 8. So, earthquakes. So that means a 9 is 100 times more powerful than a 7. A 9 is 1,000 times more powerful than a 6. There are other ways that earthquakes are measured, and you could debate about which is more appropriate. So just to mention that there's something called moment magnitude, and what that does is it takes a look at where on the fault the earthquake actually slipped. Where did the slip happen? How big of an area slipped, and how much did it move? And think about it. You could have, what if an earthquake has a really major amplitude, so it measures high on the Richter scale, but it was really short? That might not do as much damage as an earthquake that doesn't have as big amplitude but lasts a longer period of time. So in trying to measure how big an earthquake is, there's different ways you can think about it. So the one you hear in the news, always about the Richter scale. Whenever there's an earthquake on the news, they always talk about it measured 6.3 on the Richter scale or 7.6 on the Richter scale. All right. Last little concept, we're going to talk about a tsunami. So a tsunami is a very large wave. Sometimes you see them, they're referred to as tidal waves. They have nothing to do with tides. So science doesn't talk about tsunami as a tidal wave. That's, this popular perception. It's a large wave, and it has to be caused by some major movement, okay? So here's an example of an earthquake. Now let's say this is showing an example of a reverse fault, and this whole slab got pushed up. Now let's just imagine, it got pushed up a meter. So here's a meter stick. Let's imagine the floor of the ocean, this whole floor of the ocean here, got pushed up for a meter. Well, this might be a huge piece of the floor of the ocean that all got pushed up a meter. Now, if I had this 1 meter, and if we make a box that's also 1 meter wide, and let's imagine it being 1 meter deep, if you can visualize that box, that cubic meter, that's a ton of water. A cubic meter of water is a metric ton. It's actually bigger than the short tons that we use in this country. About 2,200 pounds. Now let's imagine that I've got several square kilometers of seafloor that's all moved in this earthquake. Think about the volume of water that's moving. It's huge. So it pushes up on us. Some other possible causes. Let's imagine you've got your continental shelf going down into the ocean, and a big chunk of the continental shelf maybe breaks loose and slides down, and you have this underwater landslide. That can move a big amount of water. A asteroid impact, meteor impact, a big one, could move a huge amount of water. So now what happens? You got this wave, okay? You got a big amount of water that's moving. When it's out in the open ocean, it's not a problem at all, because it tends to have this big, long, broad shape. So if you've got a ship out here, well, the ship just kind of goes up and down with that swell, and you might not even notice it happen. Where we've got a problem is when it approaches shore. Because as it approaches shore, the sea level is getting shallower. And that means this wave, this energy, this wave is interacting with this seafloor. And the front end of the wave slows down. So if the front end of the wave slows down, the rest of the wave piles into the back, and it piles up. Maybe you've done this activity where you get a line of people and you each have a balloon, and you put the balloon between you and the person in front of you, and you're supposed to try to walk along and keep the balloons in place. And what happens if the person in front suddenly stops? Well, everybody else piles up. That's what's happening here. And so this wave, as it approaches shore, becomes huge. Okay, we're talking in places, you might be talking 30 meters, 40 meters. A 30-meter wave, that's like a 100-foot wave. That's devastating. And think about it, every cubic meter of water weighs a ton. The car in your driveway might weigh 1.5 tons to 2 tons. So 2 cubic meters of water is as much as getting hit by a car. And these things might be moving at, out in the open ocean, they go hundreds of miles an hour. Again, they slow down, but it's moving. Getting hit by a car is not usually real healthy. And you say, well, water's soft. But water's not really very soft. If you've ever done a belly flop, you know that. So we've got some huge disturbance, moves a massive amount of water. Out in the open ocean, not a problem. But as it comes to shore, it piles up, and they become some of the most destructive, one of the most destructive natural phenomena on our planet. Terribly, terribly destructive. So here's just another diagram. It shows an earthquake happened out here, moved a massive amount of water, going across the ocean. But then as it comes into the other side of the ocean, we've got devastation. All right, so that's it. Hopefully that answers a couple of questions on your test, and we're wrapping up this earthquake unit. Take care.